So here I have an example of using these two formulas. Got a $30,000 investment, that'd be nice to have, right? At 2.4% annual interest, compounded blank, and in the blank I'm going to fill in these different check marks here, okay? So we're going to do a variety of these and see what happens with each of those compoundings over a 5-year period, okay? So the first one I'm going to start off with is an annual compounding. And really with all of these n values that are finite, we're going to have to use our compound interest formula with the n in it. When we get down to the continuous compounding, that's the only one that we can use the, what I call the PERT formula, the P-E-R-T, right? Formula with the E in it. So the first one, n equals 1. So we'll go with that one first. For annual compounding, we just have A equals, now I've got to plug in all my values here. P is our 30,000. R is actually 0.024. You have to convert the percent to a rate or a decimal. And then of course T is equal to 5 right there. So we plug everything into the formula. It's going to be 30,000 times 1 plus R over N, which is 0.024 over the number of compounds, which is 1. Now, this annual compounding is kind of nice with the 1 in there. Raised to the NT, well, that's 1 times 5, right? And really, this reduces down to the other formula that we saw that doesn't even have the n's in it. It's just 1 plus R raised to the T power, right? The 1's aren't really necessary there. And so that value, now I'm going to round all of these to the nearest penny, the nearest cent, hundredth place, and so that's 30,000 times 1 plus 0.024 over, well, I don't need the over because the 1 is unnecessary there, all raised to the 5th power. So you can kind of see maybe how I entered that in, and if I hit enter, there's my value, okay? So that ends up being $33,776.997. That rounds all the way up to an even $77. Right? The 0.997, the 7 rounds a 9 up, which rounds a 9 up, which rounds the 7 or the 6 up to a 7. So it all rounds up at that point. All right, so there's our answer for annual compounding. Now, I want to go to quarterly compounding. So if n equals 4, A is 30,000 times 1 plus 0.024 over 4 raised to the 4 times 5, or you could just put in 20, right, for the power. And so I'm going to hit, if you hit the second and then the enter button on these calculators, it will copy and paste the previous equation, and you can just edit some of those numbers. So I can just hit insert, divide by 4, and I'll put 20 up there in the exponent. And I'm going to get $33,812.78. All right, so that's with quarterly compounding. So definitely it went up. What's that, like from 80 to, I don't know, it's like 35 bucks, right? You made about 35 extra bucks doing that. Let's go to monthly now. So if n is 12, we're going to have 30,000 times 1 plus 0.024 over 12. 12 times 5 is going to be 60, the 60th power. And so I'm just going to copy and paste that. I'm going to put a 12 in the denominator and make the numerator, or make the exponent a 60. And I should get 33,820 $3.85. So what's that, about an $8 increase. And if I wanted to go to daily, if n is 365, then again you get the 30,000. 1 plus 0.024 over 365 raised to the 365 times 5 power, and I don't actually know what that is, so I'm going to have to type that in up here. So I'm going to change my 12 down to, over to 365, so I need 36, insert a 5, and then my power up here is going to be 365 times 5. And that gives me 33,824 and 77 cents. So that gives you another $4, okay, almost. Okay, so you can kind of see how this is increasing, but what's going to happen is as you keep increasing here, hourly, minutely, secondly, it's going to start to level off. It doesn't increase without bound entirely forever. This is definitely starting to level off, right? It's a big jump and then a smaller jump and then an even smaller jump, and it'll be a smaller jump and a smaller jump, smaller jump. By the time you get down to continuous compounding, that's kind of the max. It's kind of where it ends, right? You've hit an infinite or nearly infinite number of compounds, so it can't go any more than that. It wouldn't make sense. And so as n approaches infinity, we say that a is equal to, now here we have to use the new formula. It's 30,000 times e to the RT. So the R is the 0.024 times 5. Right, that's all up in the exponent. And so I go to my calculator. This one I'm going to have to type in 30,000 times e. Now your calculators have a couple E buttons. This one down here, the second feature of your LN button, if you are using a TI-85 or I'm sorry, TI-84 or similar, will put an exponent in for you. There's another button here over the divide. It's the second feature of the divide button, which just puts the E in, and then you have to manually put the exponents. I like the other one. It's one less step. And I put 0.024 times 5 up there in the exponent, and I get a value of $33,824.91 when I round it off. Okay, so you can see that at this point you're increasing from 365 compounds to an infinite number of compounds. So that's a large increase, right? But you're not getting that much more money. You're getting about 14 extra cents. So not a huge extra increase in the money, even with a huge increase in the number of compounds. So there is sort of this limiting factor. Okay, and so you can kind of see how to calculate all these things, what the trends are here. So it does increase very quickly, but then it kind of levels off as the number of compounds increases. Now, what's interesting about these two formulas is you can really solve for any of the variables in there. You know, for instance, if I knew what I wanted my final amount to be over, you know, maybe I was putting money away for my kids' college or something like that, right when they were born, and I wanted in 18 years, I want to have a certain amount, right? So I want the final value to be a certain amount, and I know the time is 18 years, and I already know the account, the rate, because I can look that up on the bank's website or whatever. And so I can get the rate and the compounding and all that stuff. Then I can figure out how much I need to deposit or invest in order to make that happen at the end. So that's a little bit of a tweak to this problem, where you're solving for the principal rather than for the final amount. And so in a situation like that, it would look a little bit different. But let's say you wanted to have $50,000 at the end of 18 years. at, let's say you had 1.5% annual interest compounded monthly. Okay, so I'm just throwing that up there real quickly. So what I want to do then is find the original principal that I need to get $50,000 at the end of that time period. So to do that, I plug in everything I know and solve for P. So I know the final amount is going to be 50,000, or the future value, I should say. P is unknown. R is this interest rate, which converted to a decimal is 0.015. N, we're compounding monthly, so that's a 12. This N is also a 12, and the T is my 18 years. Now remember that T is always in years. If for some reason you're given information in months or days, you have to convert that into years, okay? And now from this, I can do a couple quick calculations. And really, the main thing is whatever this thing, other than the P, whatever that turns out to be, in order to solve for P, I just divide both sides by that. Your textbook actually creates a new formula for this, which you may or may not want to use. I'm not going to have you learn a new formula necessarily, but basically it's P equals A over all this other stuff, okay? And so you're dividing the A by the rest of this other factor to get P, which is fine. So you could write this as P equals 50,000 divided by all this other stuff, 1 plus 0.015 over 12 raised to whatever 12 times 18 is, okay? And so you plug that into your calculator, and that will give you your principal that you need. So let's do 50,000 divided by, now this is a bit complicated, but I want a parenthesis, 1 plus 0.015 over 12 raised to the 12 times 18 power. I don't know if you'll be able to really see all of this, but there's my 50,000 divided by, then I've got the base there of 1 plus 0.015 over 12, and then I've got my power of 12 times 18. So, and it looks like a value similar to what we've been calculating in the other example, $38,175.41. So if I were to invest about $38,200 initially, that's going to grow to $50,000 over an 18-year period at this 1.5% annual interest. So that's a pretty significant, you're almost making $12,000 off of that just in interest over that 18-year period, which is kind of neat. So a neat way to find a principal if you know what the final value is that you're looking for. And of course you can always solve this, you can do the same thing with this formula. You can solve for P, and you can turn it into P equals A divided by E to the RT if you wanted to find a formula for the principal if given the future value, okay? And here, of course, same idea. If you solve this for P, you end up with P is equal to A over 1 plus R over N to the NT power. So you're just dividing by this other factor with the exponent on it. Again, I'm not real interested that you guys can memorize or know these formulas. In fact, I'm going to be giving you all these formulas on your tests, so I'm not expecting you to know them all. But I don't know that I probably wouldn't even give you this formula and this formula. I would just have you plug stuff into the other two and solve for P It's just one step division once you get the numbers plugged in.